Hi, this video is a part of Machine Learning from Scratch playlist. In this playlist, I explain different machine learning algorithms implemented from scratch using Python. You can download the relevant Python files from the link given in the description of each video. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that you people can read the notebooks and Python files and understand them yourself and of course re-implement them yourself. I'm expecting my audience to be well versed with machine learning general understanding and they just need little hints for implementing such algorithms from scratch. Now in this video, I'll explain development of advanced nearest neighbors algorithm based on spatial clustering. In case of regression, simple nearest neighbors outputs the weighted average of its closest samples. The weight in that case is dependent upon only the distance. Greater the distance, less will be the weight of that training samples and vice versa, of course. However, in this implementation, along with this simple approach, we will use additional information of spatial clustering. If spatial clustering is greater, then weight value should be less and vice versa. Why? Because if spatial clustering is greater, it means nearest close by in that neighborhood in close by test point or test sample, there are a lot of training samples available. So we have to give less weights accordingly. Let's understand this idea in depth. Okay, to understand this idea, basically we have to look at the data. Suppose I'm taking two input features, call them x and y. So I have two-dimensional data, and we have output value for that data. Consider these blue points to be training points and these orange points to be testing points. Now of course these blue points are very few, so consider these to be 470 samples only, and we have to interpolate this blue point data in this whole space. So for testing point we have 78,000 samples. So it's a very simple case of what you call imbalanced data set, where we have only 470 samples for training data, but we have to predict 78,000 samples. Now if you look at the data, there are some areas, for example, look at this area where there is spatial clustering. For example, for this orange point, there are nearby greater number of samples available than this orange point. At this point, there is only one sample point. Usually, it will be greater than that, but for illustration purpose, consider only the difference and understand this idea of spatial clustering, that how it works. On the one hand, we have a lot of samples available in this region, and on the other hand, we have very few training samples available for this region. So, of course, a testing point, while looking at neighboring samples, should understand this, should take into account this spatial clustering information. So this is the basic idea of advanced neighborhood, nearest neighbors algorithm. Now, this will be the data set, and let's understand how it works. So the first step is very simple, as you know from nearest neighbors idea, that we look at the test point and train point distance from each other. So we will be having consider a matrix of 78,000 into 470, where the first row will be containing the distance of first testing point from all the 470 sample points, and using this matrix we will find the closest neighbors in some radius r, which will be given. And sometimes we are not given the radius r, instead we are given the fixed number of closest neighbors, suppose 10 or 12 or 15 or 5. So we have to look at those closest neighbors and retrieve those closest neighbors from that matrix. So we will look at both of these methods while coding. So we'll explore both of these methods. So once we have the neighboring samples, once we have the neighboring training sample for each test point, what we do is we look at the relative spatial, we find the relative spatial clustering value between 0 to 1. So it will be between 0 to 1. For each test point, we will be having a single value between 0 to 1, which will show the relative spatial clustering surrounding that test point. Greater the value, closer to 1, it means greater the spatial clustering. Closer to 0 means lesser the spatial clustering. Consider this region. In this region, all the test points will be having greater spatial clustering value close to 1. And in this region, all the test points will be having spatial clustering value of close to 0. So how will we find that? So for that, first of all, we will look at the total area of or space. In that case, we have only two dimensions. So we will look at the maximum value of x-axis and minimum value of x-axis, minimum value of y-axis, maximum value of y-axis, maximum value of y-axis. So based on these values, we will find the total area where our data training data exists, and we will look at the total number of training samples. So this will give us kind of a global spatial clustering, so like of average distance between samples. So this is like a global value. Then what we will find is that for each test point, at each test point, consider this is the test point, this is one test point, and this process will happen for all the test points. What we will find is we will look at its closest neighbors. Consider we have chosen a radius of 5 meters. So suppose this is the radius of 5 meters. In this 5 meters we have these 4 samples. So we will look at the spatial clustering inside that radius, or looking at for this sample point. So this will give us the local spatial clustering value for this sample point, for this test sample point. Now what we will do is we will call that local spatial clustering value or observation test, and the global spatial clustering value are experimental train. Consider these the names. Now, once we divide this local spatial clustering divided by global spatial clustering, it will give us a value representation of spatial clustering for that specific sample point, test sample point. So greater this local spatial clustering, so means greater spatial clustering, but we want the value between 0 to 1, so we will normalize it. How we will normalize it, it's very easy. I'll explain it in code. Now, finally, how we will decide the decay membership based on this spatial clustering, how we will incorporate this spatial clustering information. For that, we will create bins between 0 to 1. Suppose we have created a bin which contains value from 0 to 0 0.1, 0 0.1 to 0 0.4, 0 0.4 to 0 0.7, 0.7 to 0.8, 0.8 to 0.9, 0.9 to 1. So we have total number of 3, 4, 5, and 6. We have total number of 6 bins in that case. Now what we will do is we will assign a weight decay membership value for each of this bit. If the spatial clustering is equal to 0, so what we want, the weight decay value should be equal to 1. If it is 0.1, it should be 1.5. It is 0.4, then it should be 2. In the same way, it is 1. If it is 1, it should be 20. Now, what about between ranges? What if the value is between 0 to 0.1? Or 0.1 to 0.4, consider a value of 0.2 or 0.3. So what will happen? For such in between ranges, we will go linearly from one bin to next bin. Consider we want to find the weight decay value for 0.2 and 0.3. Now we know that for 0.1 the weight decay value is 1.5. For 0.4 the weight decay value is 2. Now we want to go from 0.1 to 0.4 and find out the value in between. So we will go from 1.5 to 2 linearly to find out the weight decay value. So it will be between 1.5 to 2. But how will we find it? We will find it using a linear equation, like simple linear equation, b minus a divided by, there is a range. I'll explain it in code. It will be much easier to explain there. I hope so. It makes sense now. The only difference is finding this spatial clustering a bit tricky part. And once we found that, then we have to adjust the weight decay value based on different spatial clustering bins or different spatial clustering values. I think so. It makes sense now. Okay, so I call that adaptive inverse distance weighting method. So the first thing that we had discussed basically was finding out this search neighborhood. So we have this radius. Given the radius, these are the training coordinates, x and y axis for training data, and this will be the distance metrics for all the testing points and training points given the distance metric, which is Euclidean distance metric. We could use cosine similarity, we could use Manhattan distance, or any other distance. You can just visit the scipy.spatial distance method where you can find all the distance metrics. Now then after finding this matrix of 78,000, 470 that I just explained, what we do is we look at all the distances which are less than equal to radius. So this will give us a matrix of 78,000, 400 having values of true or false based on this condition of distance within the range of radius or not. Okay, now what we will do is for each of the test point, we will extract the neighboring samples which are inside this range, as this range is stored in this temp array. So neighboring samples once extracted, what we will do is we will also extract the neighboring samples distance using test train distance matrix, which contains the distances of training and testing points. Now we have the neighboring samples, distances. What we will do is we will concatenate both of these arrays. So we will be having test neighbors for each sample point having its own coordinates x and y, having the neighboring samples and neighboring samples distances. Okay, this is one way of extracting the neighboring samples given the radius. Other than search neighborhood method, we can also use closest neighbor method, in which we are given the closest neighbors that we have to extract. Consider it 5. So we have number that will be given to us as an input. Now we will extract the test train distance matrix of shape 78,000, 470 as explained earlier. Now for each test point, what we do is we extract the index of those 5 closest samples after sorting it. Now we have the index number for the closest neighbor for that single test point. What we will do is we will extract those training samples using those sample numbers, those indices, and then then the distance of those neighboring samples can also be extracted using this test train distance matrix. So again, we will be having the closest neighbors samples and distance stored in this test neighbors, but this time based on the condition of closest neighbors, fixed number of closest neighbors, not the radius. Okay, now it is clear. Now come to the point. Up to this point, this is the main methods which are used in simple nearest neighbor search, simple nearest neighbor method. But if we want to include the spatial clustering, we use this method of relative clustering value. So what we do is, first of all, for each of the test point, we calculate the mean distance for all the neighboring samples for that test point. So lower the mean distance of neighboring sample for that test point means that there is a greater it means that they are far away from this test point, so there is a less spatial clustering. Greater this distance, greater this mean value, greater will be the spatial clustering. Now once done that, so this is like storing the local spatial clustering that I explained. Now, what we will do is we will also store the global clustering value one time, and that will be equal to calculating the area based on x min, x max, y min, y max, and total number of samples. And we will divide it. We'll use that formula that is just for numerical purposes. The main idea is same. And then what we do is we will look at this relative dispersion value. We'll divide our observation test divided by our experimental train, and then to normalize it, what we will do is we will look at this relative dispersion value minimum and relative dispersion value maximum, and then we will normalize it using this formula, minus r min divided by r max minus r min. This will give us an output between 0 to 1. Once we have this relative clustering value between 0 to 1 for each test point, what we will do is we will find out the membership or weight decay value, and that will be done using these two functions. These two function is actually explaining the linear movement from one bin to another bin, as I explained. So this is like b minus x divided by b minus a, and this is 1 minus this above function, which is b minus x divided by b minus a. So let me explain. So we are given the bin value in which for which we want to find out the membership. The x actually contains the value between 0 to 1, a value of spatial clustering for that, for some test point, and this ranges will be actually containing the what you call let me show you. These are kind of ranges. So these are weight decay values. So weight decay value will be equal to the single list containing all these values: 1, 1.5, 2, 2.5, 3, 20, 10, 20. Okay, so this will be the ranges. So what we do is we will look at the value of x. If the value of x is equal to ranges I, which means if it is equal to the range between 0 to 1 values, whether it be 0, 0.1 or 0.4, 0.7, 0.8, 0.9 or 1, we will give it the weight decay value of 1 or 1.5, 2, 2.5, 3, 10 or 20. But if the decay value is in between a to b, what we will do is we will use this function 1 and function 2 to find out the in-between values, which will go linearly from the previous value to the next value. The previous value will be stored in a, the next value will be stored in b, and we will use this formula b minus x divided by b minus a. This is just a simple mathematical formulation for going linearly from one point to another. Now comes the predict method. How we will predict after fitting this method. So I think before prediction, let's explain the fitting method. So how we will fit? So we are finding the closest neighbors. We are applying the closest neighbor method. So once we have the closest neighbor for each test point, what we will do is we will look at the simple inverse distance weighting Boolean condition. If it is true, it means we don't need to incorporate the spatial clustering information. We can directly predict by applying the predict method, which I'll be explaining for simple inverse distance weighting method. But if we have to use this spatial clustering information, then what we will do is, again, we will extract the train coordinates. We will find out this relative clustering, and we will find out the weight memberships by applying this membership function in all of the for all of the test points using their relative clustering values. I think so it is clear for now. Now for prediction, what we will do is we will look at each of the test point. For each of the test point, we will look at its neighbors grades. Suppose for a single test point we have 5 closest neighbors, so these grades will be containing 5 values of neighboring samples grades, and dist variable will contain the 5 neighboring samples distances from this test point. So if the distance of testing neighboring samples to the nearest training sample is equal to 0, it means they both are same. So the prediction for that testing point should be the same as that training point grade, because they are basically same points, and we are trying to predict the training sample. So it makes sense that we should output the same grade. Okay, so then we continue for the next point to be predicted. But suppose that is not the case, and it will usually be not the case, and sometimes, very rarely, it becomes the case where a testing point and training point has distance of 0. It means they are overlapping. Otherwise, we will look at the condition. If the condition of simple IDW, which means if you want to apply simple inverse distance weighting method, then the weight should be simply 1 divided by distance into power, like power will be given as an input, whether it be 2, 3, 5, whatever the power is. So greater the distance, lower will be the weight value, lower the distance, greater will be the weight value. And how it will decay? It will decay depending upon this power value. If the power value is greater, so it will decay very fast. If power value is lower, so the decay will be low. Okay. Okay, if we want to incorporate this spatial clustering information also, so then we have to look at that based on that spatial clustering, the decay should be different, and that decay will be stored and will be given as an input after finding out in that function of membership, this weight decay membership. Okay, so we will use that weight decay membership function power for each testing point separately. In this case, the beauty is that for each testing point, the decay is different based on its spatial clustering. Okay, after that, we sum all the weights. We find out the final weights by dividing weights by dividing weights and weight sum, and then we predict it by multiplying this final weights into weight. This is like a weighted linear combination. So I think so. This whole thing is really clear. The fitting method and predict method is very much easy to follow, and even this membership method is easy to follow once you have understood the previous explanation that I have done in the Microsoft board. I think so. It makes sense now. I know it is a bit tricky based on this relative clustering value kind of thing that I have incorporated, but I think so. If you have followed that, then simple inverse distance weighting method or simple nearest neighbor will be not a problem for you, and you can easily implement that.